Okay. So, hi everyone. So, good evening all. So, first of all, let me know whether audio and video everything is clear. First of all, let me know whether audio and video everything is clear. Yes. So, those who are present in online, okay. So, please let me know whether audio and video is everything clear. Yes. Good evening, Sri. So, it's clear, right? Okay. Okay. So, good evening, Krishna. Right. Okay. So, in the previous session we have started with the conductors topic, right? And we have studied the properties of the conductors. So, which type of conductors we have studied here? So, that is nothing but isolated. We have studied about the isolated and perfect conductors under what? Under electrostatic equilibrium condition, right? Okay. So, we have studied the properties of a conductor which is nothing but isolated and perfect under electrostatic equilibrium condition, right? So, what are the properties that we have studied here? So, the first one is, see, these properties are very, very important here. So, one basic thing you have to understand is, in a conducting material, the charge carriers are free to move inside a conducting material. So, only because of this property, we are getting all the other properties of the conductors, right? Okay. So, the first property is the conductor will never ever allow for the net electric field to exist inside the conducting material. So, always the net electric field inside the conducting material is equal to 0. This is the first property. And what is the second one here? If you try to charge a conducting material, that charge will go and reside only on the outer surface of the conducting material. Understood? So, which means rho v for a charged conductor, rho v is always equal to 0, whereas rho s is not equal to 0, right? So, this is the second property. And third one is, so whatever the charge that is distributed on the outer surface of the conducting material, so it is going to distribute in such a manner that the net electric field, it is going to make the net electric field inside the conducting material is equal to 0. Understood? And the charge that is distributed on the outer surface of the conducting material is inversely proportional to radius of curvature. It depends upon the radius of curvature at that particular location, right? So, this is the third property we have studied. And then fourth one is, the electric field is always normal to the conducting surface. Always the electric field is normal to the conducting surface. That is the fourth property we have studied. And fifth one is, a charged conducting material will always acts as what here? Equipotential body. Understood? Okay. So, a conducting material, a charged conducting material will never ever allow for the potential difference to exist between any 2 points here, right? So, which means a charged conducting material will always behave as an equipotential body. So, these are the 5 properties that we have studied from the previous session. Okay. So, based on this in today's session we try to solve some problems here, right? Okay. Okay. So, let us see. Okay. So, this problem I have given you yesterday, and I asked you to try this one here. I have asked you to try this problem, right? Okay. So, what is the problem I have given here? The electric field strength at a distant point P due to a point charge plus Q located at the origin is 100 microvolt per meter. The point charge is now enclosed by a perfectly conducting hollow metallic sphere whose center is at the origin. Then the electric field strength at the point P outside the sphere becomes option A 0, option B 100 microvolt per meter, option C minus 100 microvolt per meter, option D 50 microvolt per meter. So, what is the answer here for this question? Tell me. So, what they are saying is, you are having a point charge plus q at the origin. So due to that point charge at some point P, the electric field is nothing but 100 microvolt per meter. Now this point charge is enclosed with a hollow metallic conducting sphere. Understood? Whose center is at the origin, which means this plus q charge is present at the origin now. Right? Okay. Okay. Yeah. So once you enclose this charge with a hollow metallic conducting sphere, then what happens to the electric field at point P? Will it remain same, or it is going to change? So that's what you have to determine. Right? Okay. So whether the electric field at point P after enclosing the charge with a hollow metallic conducting sphere, whether it will become equal to 0 or 100 microvolt per meter, or it will become minus 100 microvolt per meter, or it will become 50 microvolt per meter. So what is your answer here? Tell me. So if anybody has done this problem, please let me know the answer, what you got. I have already given this problem here. I have given this problem yesterday itself, right? And I asked you to try this one. So if anybody has done this problem, please let me know. Please let me know what is the answer you got. Tell me here. Sri, I hope you have attended yesterday's class, right? Okay. So Leela Krishna, right? So tell me here. Tell me, what is the answer here? Right? Sri has given 0, Leela Krishna has given B. Okay. So Leela Krishna has given option B as answer, right? And Sri has given 0 as the answer, right? Okay. So let us check which one is correct, right? Okay. See here. Here they are saying that plus q charge is placed at origin here. So let us say this is origin, right? So due to this plus q charge at some point P, so at some point P at this location, electric field is equal to 100 microvolt per meter, right? We know that due to a point charge q, the electric field at this point P is nothing but what? Let us say the distance from here to here. Let us say the distance from here to here is r here. Right. So in this case, what is the expression for electric field here? Electric field expression is nothing but q by 4 pi epsilon r square. Its value is equal to 100 microvolt per meter. Right. So this is what they have given. Right. So now what they have done is, now they have enclosed this. Now they have enclosed this charge with what? With a hollow metallic conducting sphere, right? Okay. Okay. So with a hollow metallic conducting sphere like this, right? Okay. Or otherwise I will. A hollow metallic conducting sphere. So this is a hollow metallic conducting sphere, right? Okay. Okay, yeah. So this is the hollow metallic conducting sphere. So its center is also at the origin. So now once you enclose this charge plus q with a hollow metallic conducting sphere, then what will happen here? So whenever you place a plus charge q here, so what is going to happen? It is going to radiate electric field or not? Yes or no? So it is going to produce an electric field which is radially outward. So plus Q is going to produce the electric field which is radially outward here. So that means it is going to produce the electric field like this. So the electric field lines will move away radially from plus Q charge, right, like this. Right. Right. So here plus Q charge is present. Here plus Q charge is present, right? So this is enclosed by this hollow conducting sphere. So now this plus Q is set up some electric field, right? So whenever it has set up here electric field, what will happen here? So this electric field is going to exert the force on the charge carriers, on the free charge carriers within the conducting sphere. Yes or no here? So what will happen? So this electric field is going to attract the negative charge carriers towards what? Towards this inner surface of the conducting material. See, yesterday I have told you. So if you are having the electric field, that field is going to exert the forces on the free charge carriers within the conducting material. Yes or no? So the electric field is pointing in this direction, means all the negative charge carriers within the conducting material are going to experience the force against the field. So that means in this direction they are going to experience the force. Negative charge carriers are going to experience the force against the field, that is in this direction, right? Okay, but they are not allowed to come out of the conducting material. So what will happen? So all the negative charge carriers are going to experience the force against the field. So that means they will come and accumulate on the inner surface. Yes or no? All the negative charge carriers will come and accumulate on the inner surface of the hollow metallic conducting sphere, right, like this, right? Okay, so then what will happen here? What will happen on the outside, on the outer surface of the conducting sphere? There will be a deficit of negative charge, so that you can account as what? That you can account it as a positive charge, right? So on the outer surface you are going to have what? You are going to have positive charge. See, it is same as what? It is same as the first property which we have studied yesterday. Yes or no? Whenever you subject a conducting material to an electric field, what will happen? The migration of charge carriers will takes place, right? Okay, so because of that migration there will be a induced electric field which is exactly opposite to the actual electric field, and it is going to nullify the electric field, and thus it is going to make the net electric field inside the conducting material equal to 0. See here the electric field, actual applied electric field is pointing in this direction. Yes or no? It is pointing in this direction. Now within the conducting material, here positive charge is accumulated on the outer side, and on the inner side negative charge is accumulated. So the electric field is going to point in this direction. So the induced electric field is going to point in this direction, and applied electric field is pointing in this direction. So the net electric field inside the conducting material, is equal to what? Is equal to 0. Always it must be equal to 0, right? Okay, yeah. So now see here, now what happens? Now outside the conducting sphere here, you are having what? You are having positive charge. So what will happen? So it is going to set up the electric field outside the conducting sphere. It is going to have the electric field outside the conducting sphere, right? Yes or no here? See, outside the conducting sphere you are having what? Positive charge. So because of this, what will happen? There will be an electric field outside the conducting sphere like this. So that means outside also the electric field is going to be present. So that means here, once you enclose the charge with the hollow metallic conducting sphere, the electric field here is not equal to 0. It is going to be present, right? Now we have to determine what is the electric field at that location, right? Okay, yeah. So now how to determine the electric field at that location here? So for that we are going to apply Gauss law here. Right? Okay, yeah. See here, So now what I am going to do here is So what I am going to do here is with this radius here, with this radius, that is r, with this radius r, with this radius r, I am going to form a Gaussian sphere. With this radius r, I am going to form a Gaussian sphere like this, right? Okay, so I am going to form a Gaussian sphere. So I hope you know Gauss law here. What is Gauss law here? Gauss law is nothing but the electric flux that is leaving any closed surface must be equal to the charge enclosed by the closed surface divided by epsilon. I hope you know Gauss law here, right? So now with this radius r, I have formed what? I have formed a Gaussian sphere. So this is nothing but Gaussian sphere, right? Okay. So with this radius r, I have formed a Gaussian sphere like this. Now the electric flux that is leaving this Gaussian sphere, the electric flux that is leaving this Gaussian sphere must be equal to what? Must be equal to the charge enclosed by that Gaussian sphere divided by what? Divided by epsilon, right? Okay, okay. So now just apply Gauss law here. So what is Gauss law? The electric flux, so this is nothing but Gaussian sphere. Okay, okay. So the electric flux, Gauss law, from Gauss law, we know that the electric flux that is leaving any closed surface must be equal to what? Must be equal to charge enclosed by that closed surface. So charge enclosed by that closed surface divided by what? Divided by epsilon. So here you have to write what is the charge enclosed by this Gaussian sphere. What is the charge enclosed by this Gaussian sphere? So what is the charge enclosed by this Gaussian sphere here? Tell me. So here on the outside of the sphere, what is the charge that is present? Let us say this is the inside the sphere here. Let us say inside the sphere, the charge induced inside the on the inner surface of the sphere is, let us say, Q induced on the inner side. I am writing it as Q induced on the inner side. And on the outer side of the outer surface of the conducting material, let us say the charge induced is Q induced on the outer side, right? Outer side of the surface. And here what you are having at the center here, you are having plus Q charge, right? So the electric flux that is leaving this Gaussian sphere must be equal to charge enclosed by this Gaussian sphere. So what is the charge enclosed by this Gaussian sphere? Is nothing but Q induced on the outer surface of the conducting sphere and Q induced on the inner surface of the conducting sphere plus what? Plus this charge, that is plus Q. Understood? Okay. So I am writing the total charge here. I am writing the total charge. So that is Q induced on the outer surface of the sphere plus what? Plus Q induced on the inner surface of the sphere plus what? Plus Q, which is at the origin, right? So this is the total charge here. So now tell me, this Q induced on the outer surface, this Q induced on the outer surface plus Q induced on the inner surface is nothing but what? Is nothing but net induced charge. Is nothing but net induced charge. So tell me, the net induced charge always must be equal to what? Tell me here, Sri and Leela Krishna, tell me. So net induced charge is must be always equal to what? The net induced charge must be always equal to what? Tell me. Tell me here. So if you are having a conducting material here, so if you subject this conducting material to an electric field like this, right? Okay, so then the electric field is going to point like this, right? Okay, so here inside you are going to have the applied electric field. This is applied electric field. So migration of charge carriers will take place. Here there accumulates negative charge, here there accumulates positive charge, and inside there induces an electric field, and thus net electric field is equal to what? Equal to 0. So the charge that is induced on this side is negative charge, and the charge that is induced on this side is nothing but positive charge. So this is nothing but what? Net induced charge. What is the net induced charge here? Is equal to what? 0 or not? See, we are not supplying any charge to the conducting material. Yes or no? That means it is still neutral. Just we have separated the charges. Yes or no? We have separated negative charge and positive charge. Because of that, there develops an induced electric field. Yes or no here? So the induced electric field is always due to what? Is always due to the separation of the charges. Right? Here you have not supplied or you have not created any charge imbalance within the conducting material, which means the net charge within the conducting material must be always equal to 0. Understood? Okay. So which means here the net induced charge here, the net induced charge must be always equal to what? Must be always equal to 0. So that means Q induced outer plus Q induced inner must become what? This must become equal to 0. Right? So if this becomes equal to 0, then what is the then what is the electric flux that is leaving the Gaussian sphere here? Gaussian sphere is equal to what? Will become simply Q by epsilon. So this 2 will become 0. If you add this 2, the net charge will become 0. So what is the charge you are going to left out? That is plus Q. So plus Q by epsilon. Right? Okay. Okay. Yeah. So now see here. So now here the electric field here, the electric field is radially outward. Yes or no? The electric field is the direction of the electric field here on the surface of the Gaussian sphere. If you observe, the direction of the electric field is radially outward. Right? Okay. Okay. Yeah. And if you consider the small differential area on the surface of the Gaussian sphere, if you consider a small differential area on the surface of the Gaussian sphere, so the direction of the small differential area on the surface of the Gaussian sphere is also going to point in which direction? It is also going to point in AR cap direction. So take the surface of sphere. On the surface of the sphere, if you draw a normal here, it always points along radially outward. Right. Now if you consider a small differential area on the surface of the sphere, if you draw a normal, it always points along radially outward direction, that is AR cap direction. Right? Okay. Okay. Yeah. So that means here the direction of the electric field, is in AR cap direction, and the direction of the small differential area on the surface of Gaussian sphere is also in AR cap direction. Okay. And if you observe here, each and every point on the surface of the Gaussian sphere, is at the same distance r, Yes or no here? Each and every point on the surface of the Gaussian sphere is at the same distance r, which means the electric field is going to be constant over this surface of the Gaussian sphere. So 3 points you have to observe. One is the electric field is radially outward, and the direction of the surface is also radially outward, and the electric field is constant over this Gaussian sphere. So these 3 points you have to observe. Right? Okay. Okay. Here. So from this, now we can easily solve this problem here. Now here the electric field is pointing in AR cap direction. The differential area, that is the small differential area on the surface of the sphere, is also pointing in AR cap direction. So this dot product will get simplified. So you are going to get closed surface integral E into dA, which is equal to Q by epsilon. And this electric field is constant. Yes or no? It is constant over the surface of what? Over the surface of Gaussian sphere. Right? Okay. So over this surface, the electric field is constant. So which means you can take it out of the integration. Yes or no? It is constant with respect to this integration variables. So you can take it out of the integration. So then you are going to get what? E into closed surface integral dA, which is equal to what? Which is equal to Q by epsilon. So what is this closed surface integral dA here? This represents what? This represents the surface area of the sphere, that is Gaussian sphere. So this represents the surface area of Gaussian sphere. Right? Just substitute the surface area of Gaussian sphere here. What is the surface area of Gaussian sphere? Is nothing but what? 4 pi r square. Yes or no here? Okay. So this is the radius. This is the radius of the Gaussian sphere. So the surface area of the Gaussian sphere is nothing but 4 pi r square, right? Okay, so 4 pi r square. So you are going to get E into 4 pi r square is equal to what? Is equal to Q by epsilon. Therefore, E is equal to what? E is equal to Q by 4 pi epsilon r square, right? See, before enclosing the charge, with a hollow metallic conducting sphere, what is the electric field they have given here? 100 microvolt per meter, which is nothing but what? Which is nothing but Q by 4 pi epsilon r square. The electric field due to a point charge before enclosing with a metallic sphere is equal to what? Q by 4 pi epsilon r square, which is equal to 100 microvolt per meter. So after enclosing with a metallic conducting sphere also, we got the electric field. We got the electric field expression as what? We got the electric field expression as Q by 4 pi epsilon r square, which is same as what? Which is same as before enclosing the charge with a metallic conducting sphere, right? So that means here this value must be same as what? It is equivalent to 100 microvolt per meter. Yes or no? This value is nothing but 100 microvolt per meter. So that means before enclosing this with a metallic sphere and after enclosing it with a metallic sphere, the electric field at point P is not changing. It remains what? It remains same, that is 100 microvolt per meter. Okay, so is this problem clear here? Tell me. Is this problem clear? So Leela Krishna, you also changed your answer to 0. Now tell me here. Now tell me, is this problem clear? See, in some books here, they have given the answer as a 0 here. That is wrong, right? In some books they have given answer as 0, which is absolutely wrong. So the answer for this question is 100 microvolt per meter. So I will prove that one also. See here. See here, whenever you place a charge Q here, right, and you are enclosing it with a hollow metallic conducting sphere like this, right? Okay, so so the negative charge will get induced on the inner surface, right, and equivalently positive charge will get induced on the outer surface, right? Okay, okay, yeah. So now now I am considering this is nothing but what? This is nothing but Q induced over the inner surface, right? Okay. So now we know that inside the conducting material here, so I'll draw somewhat bigger like this, right? Okay. Okay. So inside the conducting material, we know that the net electric field must be always equal to 0, right? Okay. So the net electric field must be equal to what? Must be equal to 0 inside the conducting material. That we know here. Okay. The conducting material will never ever allow, right? The isolated perfect conducting material will never ever allow for the electric field to exist inside the conducting material. So electric field must be equal to 0 inside the conducting material, right? Okay, okay, yeah. So now see here. Okay, now see here. So now here, let us say the radius here, the radius of this sphere, is capital R. Let us assume the radius of this sphere is capital R, right? Okay, okay. So now what I am doing here is this thickness is very, very small here. This thickness of the conducting material is very, very small, right? So I am considering at this point. So that is inside the conducting material. Inside the conducting material, I am considering the point. So still the distance from here to here is almost what? Is almost same, because the thickness of this conducting material is very, very small. We can neglect here. It is very, very small. Understood? And hence the distance from plus Q to this point is also nothing but R only. Now what I am doing here is with this radius capital R, I am going to form the Gaussian sphere. I am going to form the Gaussian sphere, or I can say Gaussian surface inside what? Inside the conducting material. So this is the Gaussian sphere here, right? Okay. So I am forming the Gaussian sphere like this. Okay, so this dotted line, purple color or violet color dotted line is nothing but Gaussian sphere, right? Okay, so now if I apply Gauss law, what is Gauss law here? What Gauss law says? The electric flux that is leaving any Gaussian surface must be equal to the charge enclosed by that Gaussian surface. So the electric flux that is leaving this Gaussian sphere, now the electric flux that is leaving this Gaussian sphere must be equal to what? Must be equal to charge enclosed. What is the charge enclosed by this Gaussian sphere here? Is nothing but Q induced inner plus what? Plus this Q, right? So this is equivalent to Q induced over the inner surface of the conducting sphere plus what? Plus Q divided by epsilon, right? Okay, and we know that inside the conducting material the electric field must be always equal to what? Must be always equal to 0. So if you put here electric field, electric field is equal to 0. We are considering the Gaussian sphere inside the conducting material. Inside the conducting material, electric field must be equal to 0. So if you put electric field is equal to 0, then this term will become equal to 0. Understood? So if this term becomes equal to 0, then Q induced inner will become equal to what here? Will become equal to minus Q. Right? Okay. So that means here whatever the charge that is induced on the inner side of the conducting material is equivalent to what? Is equivalent to minus Q. So now we know that the charge that is present on the outer surface of the conducting material must become what? Q induced outer must be equal to what? Must be equal to plus Q. Why here? Because the summation of these two, that is the net induced charge must be always equal to 0. So that means if you place plus Q charge here, right, then the charge that is going to induce on the inner surface is must be equivalent to minus Q, and the charge that must be induced on the outer surface must be equal to what? Must be equal to plus Q, right? Okay, okay. So this is the value of the induced charge on the inner side of the conducting sphere, and this is the value of the induced charge on the outer surface of the conducting sphere, right? Okay, okay. Okay. So is this clear here? Tell me. Okay. Okay. Right? Okay, okay. So in some books what they have done is they have represented only Q induced inner here. They have represented only Q induced inner, and they have not represented the charge that is induced on the outer surface of the conducting material. And if you don't represent this Q induced that is on the outer surface of the conducting material, then obviously you are going to get the electric field is equal to 0, which is wrong. So if there exists a negative charge, induced charge on the inner side, means outside there must be what? There must be a positive induced charge, such that the net induced charge must be always equal to 0, right? Okay, so the electric field equal to 0 at point P is wrong here, right? Okay, okay. So I hope this problem is crystal clear here, right? Right. So for this one, the correct option is option B, 100 microvolt per meter. Okay, okay. Okay, right. Okay, here. So if you are having any doubts, you can ask me here. Otherwise, we will move on to next problem. Shall we move on to next problem? Tell me. Sri Leela Krishna. Yes. Okay. 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 So next problem. Right. Sri, is this clear? Sri? Right? Okay. So next problem, I have given this one here, right? So what is the problem? See here, two metallic charged spheres of different radii are raised to the same potential of 6 volts. Then the ratio of their surface areas is. So I have given two metallic charged spheres of different radii are raised to the same potential of 6 volts. Then the ratio of their surface areas is, right? Okay. Okay. So now see here. So it is very simple problem here. So let us consider two spheres here, two metallic charged spheres. Okay. So this is one sphere. Let us say the radius of this one is R1, right? So this is one sphere, and I am considering another sphere because they have said two different spheres. So I am considering another sphere of radius R2, right? Okay. And they are saying that these two are nothing but charged spheres, right? So that means you have supplied the charge to this sphere as well as that sphere. Let us assume the charge on this sphere is Q1. Let us assume the charge on this sphere is Q1. See, whenever you supply a charge, where it will go and reside here? It will go and reside only on the outer surface of the conducting material. So this is what you have to understand always, right? And let us assume here you have supplied a charge of Q2, right? So whatever the charge you have supplied, that is going to distribute on the surface of what? On the surface of the sphere, like this, right? Okay. And how this charge is going to distribute on the surface of the sphere here? Whether it is going to distribute uniformly or non-uniformly? Tell me here. Sri, tell me. Whenever you supply a charge to this sphere, right? Whenever you supply a charge to this sphere, that charge is going to distribute uniformly on the surface of the sphere, or it is going to distribute non-uniformly on the surface of the sphere? Tell me. See, yesterday I have told here, each and everything on conductors is going to be based on the properties, whichever we have dealt in the yesterday's class, right? Okay. See, suppose if you are having the shape like this, right? Okay, if you are having the shape like this, now if you supply some charge Q to this one, so what will happen here? So here at this location, at this point, the radius of curvature is less, so that means more charge will get accumulated. More charge will get accumulated at this location, and here the radius of curvature is more, so less charge will get accumulated here, and again here more charge will get accumulated, right? So in this manner here, I have drawn some rough diagram. So in this manner the charge is going to distribute. Wherever you are having radius of curvature less, at that location more charge will get accumulated, and wherever you are having radius of curvature more, at that location you are going to have less charge distribution, less charge accumulation. Understood? So in this manner non-uniformly it is going to distribute if you take some arbitrary conducting structure like this, right? But here you are considering what? Here you are considering, okay, but here you are considering what? Sphere. So for sphere, at each and every point here, the radius of curvature is going to be uniform or not? Yes or no? The radius of curvature is going to be uniform for a sphere. So that means the charge is going to be distributed. Whatever the charge that you are going to supply to this sphere, metallic sphere, it is going to distribute uniformly on the surface of the sphere, right? Okay. Yes, Sri, that's what I am saying. Depends on the radius of curvature. But if you observe sphere here, it is having what? It is having the radius of curvature for a sphere is uniform or not? That is nothing but what? R1. Yes or no? For this one, the radius of curvature is R2. Whatever the point you will take, the radius of curvature of this sphere is going to be R2. And here, whatever the point you will take, the radius of curvature is going to be R1. So since for a sphere, the radius of curvature is uniform, so which means the charge that you are going to supply is going to distribute uniformly on the surface of the sphere. Right? Okay. So these points are very, very important here. So you should not just blindly go through the problem and get the answer. Understood? Okay, so that anybody can do, but here we have to analyze each and everything. Not only solving the problem is important, but also understanding the problem clearly is also very, very important. So that will come if you understand the concepts clearly, right? So don't be in a hurry or don't rush to give the answers. Okay, so first analyze the question, each and everything step by step, and if you are getting any doubts, you can ask me, we can interact, and I will try to clarify your doubts also, right? So that is the way of learning here. So once you become clear with the concepts, then you can play with the subject, right? Okay. 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 So here one more thing, if you are having a sphere, and if the charge is distributed, uniformly on the surface of the sphere, here you are having some sphere, and if the charge is distributed only on the surface of the sphere uniformly, right? Okay, plus q, right? So for this here, let us say the radius of this sphere is r. So for this one, I am trying to give you the expression for the electric field on the surface of what? On the surface of the sphere. So the expression for electric field on the surface of the sphere for this one is equal to q by 4 pi epsilon r square, where r is the radius of the sphere here, right? So just you have to remember these things, because I have already discussed these things while dealing with Gauss law. So that is available in Dalton Batch series EMT playlist. Okay, you can go through that. Okay, so that's why I am taking here the results directly. So on the surface here, that is at r equal to r, the electric field is equal to q by 4 pi epsilon r square, and the potential here. So if I draw the graph for the potential for this problem, if I draw the graph of potential, so V versus R, so let us say this point is R equal to capital R, that is on the surface of the sphere, and this region is R less than capital R, that is inside the sphere, and R greater than capital R, this is outside the sphere. So if you draw the graph of this one here, you are going to get the graph like this, right? Okay. Okay, so here the potential V is equal to q by 4 pi epsilon into R, and here V is equal to q by 4 pi epsilon into small r, right? Okay, okay. So here, so this is on the surface of the sphere here. At r equal to r means on the surface of the sphere, and this region is nothing but inside the sphere, right? So inside the sphere and on the surface of the sphere, the potential is nothing but what? The potential is constant. So that is nothing but q by 4 pi epsilon r, right? If you are having a uniformly charged sphere such that the charge is distributed uniformly on the surface of the sphere, then in that case the potential inside the sphere and the potential on the surface of the sphere both are going to be same, and it is constant, Understood? Okay, okay. Yeah. So whereas electric field here, so if I draw for the same problem, if I draw the electric field versus R, so this is electric field versus R. So here at R equal to capital R, this region is R greater than capital R, this region is R less than capital R. So inside the sphere, okay, so the electric field, so this I am considering as hollow here, hollow sphere, right? Okay, hollow sphere here. So this is hollow sphere, right? Okay, so for this hollow sphere, if the charge is distributed uniformly on the surface of the sphere, then inside the sphere the electric field is equal to 0. Inside the sphere the electric field is equal to 0, and on the surface of the sphere, the electric field is equal to q by 4 pi epsilon capital R square. So if you move outside the sphere, the electric field E is equal to q by 4 pi epsilon small r square, right? So this region is outside the sphere, this region is inside the sphere. Inside the sphere electric field is equal to 0, on the surface of the sphere the electric field is equal to q by 4 pi epsilon r square. So if you are having a hollow sphere and if the charge is distributed uniformly on the surface of the sphere, then this is the graph for the potential and this is the graph for the electric field. This is the graph for the electric field, right? Okay, okay. So okay, and on the surface of the sphere, the potential is q by 4 pi epsilon r, and on the surface of the sphere, the electric field is q by 4 pi epsilon r square. So just I am revising these things here. So keep these points in mind, right? Okay, okay. So this problem is very, very simple here. You can easily answer this one. So anybody got the answer here? Anybody got the answer? Tell me the answer. What you got? If anybody got the answer, please let me know. Leela Krishna has given option A. So he has given option A, that is 6. Okay. So let us check here. Let us check whether that answer is correct or wrong. Let us check, right? Okay. Okay. Yeah. So I have copied that problem here. Okay. So they are saying that you are having two charged metallic spheres, and those two charged metallic spheres have risen to the same potential. Understood? Okay. So that means the potential on the sphere S1, let us say this is sphere S1 and this is sphere S2. Okay, the potential on the surface of the sphere S1 is same as what? Is same as the potential on the surface of sphere S2, right? So that's what they have given. So V1 is equal to what? V2 is equal to, they have given it as 6 volts. Right? Okay, okay. So what is V1 here? V1 is nothing but the potential on the surface of the sphere S1. So what is the expression for the potential on the surface of the sphere S1 here? If here the charge is uniformly distributed. Yes or no? The charge is uniformly distributed. Right? Okay, how we know that? Because it is a conducting sphere. If you supply the charge, it is going to distribute uniformly on the surface of the sphere because of the radius of curvature for this one is uniform. Okay, okay. So V1 is equal to what? V1 is equal to, I can write it as Q1 by 4 pi epsilon R1. So this is equivalent to, so V2 they have given as a V2, let us assume the charge on V2 is Q2. So it will become what? The potential on the surface of sphere S2 is nothing but Q2 by 4 pi epsilon R2, which is equal to what? Which is equal to 6 volts, right? Okay, okay. So from here we can say Q1 by Q2, right? Here 4 pi epsilon will get cancelled. Q1 by Q2 is equal to what? Is equal to R1 by R2, which is equal to what? Which is equal to 6. Right? Okay. So that means from here I can say R1 by R2 is equal to 6. So this is what we got here. R1 by R2 is equal to 6. So that means the ratio of their radii is equal to 6. Now they are asking the ratio of their surface areas. Right? So let us say for sphere S1 the surface area is A1. Okay? For S1 the surface area is A1, which is equal to what? The surface area of a sphere is nothing but 4 pi R1 square, right? And for S2 here, for S2 the surface area is A2. Let us say the surface area is A2, right? Okay, so A2 is equal to what? Is equal to 4 pi R2 square. So from here what you are going to get? A1 by A2 is equal to what? Is equal to R1 by R2 whole square. So which is equal to what? R1 by R2 is nothing but 6. So substitute R1 by R2 equal to 6 here. So 6 square is equal to what? Is equal to 36. Right? So this is the ratio of the surface areas of the two spheres, which is equal to 36. Right? Okay. Here they have not specified whether you have to determine A1 by A2 or you have to determine A2 by A1. So they have not specified this thing here, right? But if you observe the options, you are having 6 here and here 1 by 6, and here you are having 36, but you are not having 1 by 36. Okay, so the only one option that is left out is nothing but 36. So you have to choose option C, right? Okay, okay. So I hope you have understood what I am saying. Here they have not specified whether you have to determine. They are simply saying you have to determine the ratios of the two spheres, but they have not told whether you have to determine A1 by A2 or A2 by A1. Understood? Okay, so determine both here. So A1 by A2 is equal to 36 and A2 by A1 is equal to 1 by 36. So among these two options they have given only one thing, so that is going to be correct. That is 36 they have given, they have not given 1 by 36. Understood? Okay, okay, right. Right. So is this problem clear here? It is very simple problem. So I hope it is clear here. So for this question, option C is correct. Option C is correct. Right? Okay. Okay. So let me know, is this clear here? Tell me, Sri and Leela Krishna. If you confirm it, then we will move on to next problem here. Is this problem clear? Yes? Okay? Okay. Okay then, fine. So we will move on to next problem. Okay? Okay. So I am expecting the answer for this problem from your side here. From your side, I am expecting the answer to this problem. Okay? Because this is a gate question here. This is previous gate question. I am expecting the answer from your side, right? So what is the question they are asking here is two conducting spheres S1 and S2. Two conducting spheres S1 and S2 of radii A and B, where B is greater than A. Okay, of radii A and B, where B is greater than A. So here respectively. Right, okay, of radii A and B respectively are placed far apart and connected by a long thin conducting wire as shown in figure. So this is the figure they have given here, right? So this is the figure they have given, right? So for some charge placed on this structure, the potential and surface electric field on S1 are VA and EA, and that on S2 are VB and EB respectively. Then which of the following is correct? Okay, what they have given here? They have given two conducting spheres S1 and S2 of radii A and B, where B is greater than A, right? They are placed far apart from one another. These two spheres are very far apart from one another. Now these two spheres have connected with a thin conducting wire here. So this is nothing but a thin conducting wire. Thin conducting wire. Okay, so once they have connected with a thin conducting wire, then what they have done is they have supplied some charge to this conducting system. Now it has formed a single conducting system. Okay, so to this single conducting system, they have supplied a charge. They have supplied a charge to this conducting system. Understood? So once they have supplied a charge to this structure, then they are asking what is the electric field and potential on the surfaces of S1 and S2, how they are related. So that's what they are asking. Okay, how the potentials and electric fields on the surfaces of S1 and S2 are related, right? Okay, so that's what they are asking here. So in option A, they have given VA equal to VB and EA is less than EB. In option B, they have given VA greater than VB and EA greater than EB. Option C, they have given VA equal to VB and EA greater than EB. And option D, they have given VA greater than VB and EA equal to EB. At least let me know which options we can eliminate here. Tell me. Which options we can eliminate? Tell me here. Which options we can eliminate? Here you are having metallic sphere S2 and here another metallic sphere S1, right? So these two are placed very far apart from one another. So these two are connected with a long thin conducting wire, right? So whenever these two are connected with a long thin conducting wire, then what will happen? This total will behave as a single conducting system. Yes or no here? It becomes a single conducting system, or you can simply say it becomes a single conducting material. Yes or no? Okay. So now what they are doing? They are supplying some charge, let us say some charge Q to this structure. So once they supply some charge Q to this structure, then what is the electric field, or how the electric field and potentials are related on the surface of the two spheres? So that's what they are asking. 3. B, D maybe can eliminate. Okay, so you are saying B and D we can eliminate. So why you are saying that means we know that once it is connected with a long thin conducting wire, then it is going to behave as a single conducting system, and we know that a charged conductor must behave as what? Must behave as a equipotential body. Yes or no? So this total system has become a single conducting material. Now if you supply the charge, to this single conducting material, then the potential is going to rise, and the potential throughout this conducting material must be same. So which means the potential of S2 must be same as what? The potential of S1. So VA must be equal to VB. Okay, that's what we can confirm. So because of that, you are saying maybe, so B and D we can eliminate. So option B we can eliminate, and option D also we can eliminate, because once it becomes as a single conducting material, then the potential must be same throughout the material, right? So which means the potential here and the potential here must be same, right? So potential here is VA and potential here is VB. So VA must be equal to what? VA must be equal to VB, right? Okay, yeah, right. So one more thing also you can guess here. You can guess for electric field also, right? So I am not saying to follow the same thing for every problem. Okay, so but here we can make a guess. Okay, anyway we are going to solve the problem, right? But here we can make a guess regarding electric field also, right? See here, so you have supplied a charge Q, right, to this structure. So whenever you supply a charge Q, what will happen is this charge is going to distribute between sphere S2 and S1, sphere S2 and S1, until the potential of this one and the potential of this one must become equal, must become same. Understood? Whenever you supply a charge Q to this conducting system, what happens here? This charge is going to distribute between S2 and S1 in such a way that the potential of S2 must be same as what? The potential of S1. So that is VA equal to VB. So let us assume once the charge distribution has done, let us assume the charge on S2 is Q2. The charge that is distributed on S2 is Q2 and the charge that is distributed on S1 is Q1. So where this Q1 plus Q2 is equal to what? Must be equal to the supplied charge Q. So this is supplied charge. Yes or no? Must be equal to Q. Understood? Okay, so this is what we can confirm, right? Now see here, if you observe the radius of sphere, S2, so this is nothing but B, and the radius of sphere S1 is nothing but what? Is nothing but A. So the charge Q2 is supplied to this one and the charge Q1 is supplied to this one, let us assume, right? Okay, yeah. So now if you observe the radius of curvature of sphere S2 and the radius of curvature of sphere S1, which one is greater and which one is smaller here? See, if you observe here, B is greater than what? B is greater than A. So which means what? Which means the radius of curvature of B, that is sphere S2, is greater than what? Is greater than the radius of curvature what? The radius of curvature of A, that is sphere S1. Understood? Okay, and we know that the charge distribution on the surface of the sphere is going to depend upon the radius of curvature. Understood? Okay, so here the radius of curvature of this one is more. That means the charge accumulation, the charge distribution, or the charge accumulation, or I can say the surface charge density on this sphere will be lesser when compared to the surface charge density on this one. Yes or no? So yesterday I have told that the charge density, the surface charge density is inversely proportional to what? Is inversely proportional to radius of curvature. Now here for this sphere S2, the radius of curvature is more. So which means the charge density over this sphere is let us say this is rho S2 is what? Is lesser when compared to what? When compared to rho S1. Right. So if the charge density is more, on the surface of sphere S1, right? Okay. If the charge density is more, this is rho S1 here, right? And here the charge is distributed like this. Let us say the charge is distributed like this. Okay, because here on this surface the charge density must be lesser when compared to this one. So for this it is rho S2. Okay, since the charge accumulation or the charge density over the surface is more, we can guess that the electric field on the surface here, the electric field on the surface S1, that is EA, is going to be what? Is going to be greater when compared to the electric field on the surface S2. Yes or no? Can we make this guess here? Tell me. EA, here EA, so on this surface it is going to be what? It is going to be EB. So since rho S1 is greater than what? Rho S2, we can guess that EA is going to be greater than what? EA is going to be greater than EB. So this is what we can guess. So VA equal to VB, this is obvious, and we can guess that EA is greater than EB. So from this here, just without solving the problem, right, just with the help of the properties, we can guess the answer, that is VA must be equal to VB and EA is greater than EB. Right? Okay. Okay, yeah. So that means which one is the correct answer here? Our guess is option C. Our guess is option C. Right? Okay. Okay. Yeah. So this type of things will be very much helpful if you are not having, if you are running out of the time in the examination. Okay. So this type of guesses are very good here. Right? Okay. Okay. So now anyway we try to solve the problem. Right? Okay. So this is our guess. Right. Let us check whether our answer is correct or wrong. Okay. So you have supplied a charge Q to this conducting system, right? Okay. Okay. So initially you are having two conducting spheres and these two are connected by a long thin conducting wire, right? Okay. And now you have supplied a charge Q to this conducting system. See, one more point you have to understand here is they are saying that these two conducting spheres are very far away from one another. So which means you should neglect the potential that is produced by this sphere at this location. Understood? See here you are having S2 like this. Yes or no? The charge is distributed like this on the surface of S2. Right? Okay. So it is going to have what? It is going to set up some electric field outside also. So outside also you are going to have some potential. Understood? Okay. So that means on S1 you are going to have what? You have to count the potential that is produced by what? That is produced by S2. Yes or no? Okay. In general this is the procedure. But here what they are saying, S2 and S1, these two are what? Very, very far away. These two are very, very far away. What they are saying, these two are connected with a very long, thin conducting wire. So which means this S2 and S1 are very, very far away from one another, which means you can neglect the potential. You can neglect the potential of S2 on S1, and also you can neglect the potential of S1 on S2. So that's what you have to understand, right? Okay, okay. So each and everything here, each and everything you must have the crystal clarity, right? Okay, okay, okay. So coming to the problem, okay. So the potential of A must be equal to what? The potential of B, right? So once you supply a charge Q, so I said this charge is going to be distributed between S2 and S1 such that the potential of S2 and S1 must become same. Okay, so let us say the charge on this sphere S2 is Q2 and the charge on this sphere S1 is nothing but Q1. So the potential of sphere S2, the potential of sphere S2 is nothing but what? Is nothing but Q2 divided by what? Divided by 4 pi epsilon. Let us say the radius is RB here. Let us say the radius is RB. Right. So for VA, the potential on this surface is nothing but what? Is nothing but Q1 divided by 4 pi epsilon RA. Right. Okay. Okay. So from here Q1 by Q2 is equal to what? Must be equal to RA by RB. Right. So this is the conclusion we can make. So this is equation number 1. Let us say. Right. Okay. Next. What is the electric field on the surface of S2 here? What is the expression for the electric field on the surface of S2? So just now I have told, if you are having a sphere and if the charge is distributed uniformly on the surface of the sphere, then the expression for the electric field on the surface of the sphere is equal to what? Is equal to Q by 4 pi epsilon R square. So this is the expression here for the electric field on the surface of the sphere. Let us assume the charge on the surface of the sphere is Q, then the electric field on the surface of the sphere is equal to what? Q by 4 pi epsilon R square. So this charge is what? This charge is uniformly distributed, right? Okay, this charge is uniformly distributed, right? Okay. So now let us say the the electric field on the surface of S1 is nothing but EA, which is equal to what? Which is equal to, here the charge is distributed uniformly on the surface of the sphere. So the electric field on the surface of S1 is nothing but what? Is nothing but charge on the sphere, that is Q1 divided by 4 pi epsilon. So what is the radius here? Radius I am considering as RA. So RA square. So similarly EB, the electric field on the surface of what? On the surface of sphere S2 is equal to what? Is equal to Q2 by 4 pi epsilon RB square. Right. Okay. So from these two I can take a EA by EB ratio. So if you take EA by EB ratio, what you are going to get? You are going to get Q1 by Q2 into what? EA by EBR. So you are going to get Q1 by Q2 into RB square by what? By RA square. Right. This is what you are going to get. So from equation 1, Q1 by Q2 is equal to what? Q1 by Q2 is equal to RA by RB. Okay. So this is equal to what? This is equal to RA by RB into RB square by RA square. So here RB, RA will get cancelled. So you are going to get RB by RA. So this is the ratio of electric field on the surface of what? On the surface of the two spheres. So EA by EB is equal to RB by RA. So here they have given that B is greater than A. So that is the radius of this sphere is greater than what? Is greater than radius of sphere A. Right. Okay. So which means B is greater than A. So that is, we have considered the radius as RB. So that is RB is greater than RA. Okay. So this RB by RA is greater than 1 here. RB by RA will be greater than 1. So this implies EA by EB ratio will be what? Will be greater than 1. So this implies EA is greater than what? EA is greater than EB. Right. Okay. So we got what? We got electric field on the surface of sphere S1 is greater than what? The electric field on the surface of sphere S2. Right? For S1 the radius of curvature is more, whereas for S2 the radius of curvature is for S1 the radius of curvature is less, for S2 the radius of curvature is more. Right? Okay. So EA is greater than EB, and the potential VA is equal to what? VA is equal to VB. Right? Okay. So I hope this problem is crystal clear here. Right? So therefore VA equal to VB and EA is greater than EB. So this is the answer for this question. Right? Okay. So which one here? Our guess is correct or not? Yes or no? VA equal to VB and EA is greater than what? EA is greater than EB. So option C is correct for this question. Right? Okay. So is there any doubts here? Tell me. Is this clear? Let me know here. Sri and Leela Prasad, let me know, is this clear? Is this problem clear? Tell me here. Please confirm whether this problem is clear or not. Yes? Okay. So, okay, I hope it is crystal clear here. Right? Okay. Okay. So, with this I am winding up the session for today. Right? Okay. So, if you want, you can try these problems as homework. So, anyway, I will do this problem tomorrow also. Okay. But after completion of the class, try to do this problem as homework here. Try this one. Right? Okay. So, this problem as homework. So, try this problem as homework here. Homework problem. Please note it down. So, what I have given here is two isolated metallic solid spheres of radii R and 2R are charged such that both of these have same charge density rho s. So, you are having two metallic solid spheres which are having radius capital R and 2R. So, these two are charged such that both are going to have what? Both spheres are going to have the same surface charge density. Right? That is nothing but rho s. Okay. So, rho s coulomb per meter square. If you want, you can write rho s coulomb per meter square. Right? So, the spheres are located far away from each other and connected by a thin conducting wire. Now, find the new charge density on the bigger sphere. New charge density on the bigger sphere. Right? Okay. So, this is what you have to determine here. Right? So, two spheres are there. Right? Both are having the same charge density. Two different spheres here. They are having different radii, but they are having the same surface charge density. That's what they have given. Now, they have connected with a long thin conducting wire. Understood? So, then they are asking what is the new charge density? Find the new charge density on the bigger sphere. So, this is what they are asking. Right? Okay. Okay. So, do this problem as homework. Right? Okay. So, note down this one here, note down this one and do it as homework. Right? Okay. So, if you solve this, it is going to be very, very good here. Right? It will be excellent if you solve this problem. Right? Okay. So, I hope I can get the answers from you in tomorrow's class. I hope so. Right? Okay. So, with this I am winding up the session for today. Right? So, today I am winding up the session for today, and tomorrow also exactly at 7:30 p.m. So, EMT class will be at 7:30 p.m. tomorrow. Yeah. Right? Okay. Okay. Yeah. Okay, so with this I am winding up the session. We will meet tomorrow exactly at 7:30 p.m. So until then, take care. Bye bye.